Okay, welcome everyone to this INQA online seminar for the 25th of February 2025. It's my great pleasure to welcome today's speaker, who is Andras Grabarits from the University of Luxembourg. And Andras will be talking to us today about counterdiabatic and non-adiabatic optimization for crossing the dreaded quantum phase transitions. Over to you, Andras.
Thank you very much for this possibility, and welcome, dear INQA audience and network. I'm going to talk about I'm going to give this talk in terms of two papers in collaboration with Federico Balducci, ex-postdoc colleague, Barry C. Sanders from University of Calgary, and Adolfo Del Campo, my PI, my advisor from the University of Luxembourg. So, as a starter, a quick outline about what I'm going to talk about. First, I'm going to test the effect of local counterdiabatic driving.
Andras, you're no longer sharing your screen.
Oh,
I don't
that's
think.
a mistake. Yeah, I'm sorry.
Yeah,
okay,
no problem.
Yeah. It's good now.
Perfect.
Okay,
Yeah.
so
Thanks.
I'm sorry. So the outline. First, I'm going to test the effect of local counterdiabatic driving in quantum annealing for NP-hard problems exhibiting spin-glass behavior and the very dangerous exponentially small quantum annealing ground state gap. For these problems, I also introduce our new novel approach, the quantum brachistochrone counterdiabatic driving, and we'll compare the two methods. As a spoiler, the first fails, the latter is quite promising. In the second part of the talk, I'm going to turn to second-order quantum phase transitions, but with a different strategy by optimizing a single control parameter to achieve faster adiabatic dynamics. Again, local strategies, local adiabatic condition-based strategies are shown to be insufficient, for which reason we again introduce a new method called non-adiabatic quantum optimization. As a quick summary on optimization and solution by annealing stochastic search, optimization problems are ubiquitous in everyday life. Most conveniently, they can be cast into the minimization of a cost function or an energy. And a very powerful method is a stochastic search called simulated annealing. However, in NP-hard problems, what typically happens that this energy cost function landscape becomes very rugged, exhibiting a lot of local minima which are nearby to each other in energy, but far away from each other in configurational space. This implies that the search gets stuck and implies, in particular, exponentially long waiting time. Another important effect is an entropy-like hardness or barrier, which says that even if one can get out of the local minima, usually it's a very smooth manifold with large high dimensionality, implying increasing proliferating amount of ways where the next step can be done. And again, this slows down the protocol. For this reason, a feasible alternative nowadays implementable in real quantum computers is the quantum annealing, in which classical fluctuations are replaced by quantum fluctuations, and the cost function is replaced by the ground state of a properly chosen Hamiltonian, which can be seen here. This is a typical quantum annealing Hamiltonian, with the first term encoding the ground state of the problem, the solution of the problem in terms of the ground state, and the second term induces the quantum fluctuations. It is usually termed as the initial or easy to prepare Hamiltonian, because during quantum annealing, one prepares the system in the ground state of this initial Hamiltonian and then tries to evolve it adiabatically towards the final Hamiltonian. If the adiabatic condition is satisfied, meaning that the driving rate is small enough, then one really successfully achieves the final ground state. However, as one can see, or as one is very familiar with this in this community, the driving rate should be proportional, inversely proportional to the square of the minimal energy gap. And the problem starts here. For spin glasses, these energy gaps, minimal energy gaps, are exponentially small. This can happen due to many reasons, such as in NP-hard problems, one faces spin glass phase behavior or many body localizations, and in most of the cases they can identify it properly with a first order quantum phase transition. Another very important characteristics is that around this critical point where the energy gap closes exponentially, states, as I already mentioned in a classical search part, states with macroscopically distant configurations become very close to each other in energy. They exchange actually the order of energy. That is where the exponentially small gap appears, as it is exemplified in this plot, where the two closed local minima have macroscopically distinct spin configurations, and this is a typical energy landscape borrowed from this paper for the XOR SAT, the 3 XOR SAT, which exhibits also an exponentially small quantum annealing gap. So the aim in this part of the talk is to speed up this passage through the first order quantum phase transition, and the tool is counterdiabatic driving. Adding a counterdiabatic term to the quantum annealing Hamiltonian, in this form, the derivative of the protocol times the adiabatic gauge potential can achieve adiabatic driving at arbitrary fast processes. The adiabatic gauge potential is by definition given by this, invented and reinvented by Demir-Plak and Michael Berry. However, for many body systems, this adiabatic gauge potential becomes highly non-local and completely hopeless to implement it in real quantum devices on quantum hardware for many body systems. So one needs to approximate it. One needs approximation strategies, which, just to mention the most popular, most feasible ones, can be done by a direct truncation, a Floquet-Krylov nested commutator expansion, or many times referred to as variational expansion, or the expansion in Krylov subspace. The latter also studied by or investigated by Adolfo. So before going to what we will apply, first a quick summary of spin glass toy model that we will use to exemplify the main features of this spin glass bottleneck first order quantum phase transition problem. This spin glass toy model is constructed like this: a frustrated spin ring with ferromagnetic couplings of unity, apart from the last two couplings, which have different values, and an opposite end and the antiferromagnetic coupling on the opposite end of the spin ring. This problem has the advantage of being exactly solvable, as we will see, has an exponentially small ground state, and unlike other exactly solvable models, this exponentially ground state is really the consequence of the macroscopic rearrangement of the instantaneous ground state, as I already mentioned. This is exemplified here. Until the critical point, but at larger values of the critical point, we have a instantaneous ferromagnetic-like ground state, apart from the X transverse field fluctuations. As we cross the critical point, the ground state will converge, however, to a different state in which half of the chain, +1, because there are an odd number of spins, as you can see, so half of the chain has gone through a spin flip, so to satisfy this antiferromagnetic coupling, So this macroscopic rearrangement and the exponential ground state makes it feasible to study the spin glass bottlenecking first order quantum phase transition. As I said, it's exactly solvable, as it can be mapped to free fermions. It can be seen here, and the free fermionic picture is the following: a simple hopping model, such that only the first and the last lattice site possesses on-site energies. That results in localized edge states. However, their overlap is exponentially small, as it can be seen in this schematic plot, which induces that before and after the critical point, their role is exchanged. Before the critical point, the left eigenstate is exponentially localized. After it, the right one is that. Because their overlap, their mutual information in a naive words is exponentially small, their energy difference at this exchange, at this critical point, will also be exponentially small, as one can see in these details here. So with this setup, we apply the variational CD approach, the nested commutator expansion. However, we use a more advanced version with locally optimizable parameters in the first and second order expansion, containing 2 and three-body spin-spin interaction terms. These locally optimizable parameters are optimized by an action principle, where this G matrix measures the distance of this approximate CD from the exact CD. This G becomes 0 for the exact CD, and it can be minimized, achieving the, let's say, such an approximate counterdiabatic driving that is closest to the exact one. However, one should specify in which distance, in which space, and the distance is the simplest one, the trace norm distance, like operator vector space distance. One can express this distance and minimize it via the functional derivatives with respect to the parameter-dependent local expansion coefficients. They are 2 or 3 line long equations that can be solved numerically, and we did it, and we measured or investigated the effects of this approximate counterdiabatic Hamiltonians via the kink number, or better to say, the number of violated bonds, the number of neighboring spins that are aligned opposite to how they should in the ground state. So basically, which violates the half-half ferromagnetic order, as I showed in the previous slides, and the opposite directed alignment along the anti-ferromagnetic coupling. This kink number is very useful because it identifies the regimes where the final fidelity is finite. That is when we have less than one kink, less than one violated bond. However, when we have an extensive proportional to the system size kink number, that means a complete breakdown of adiabaticity. The numerical result is the following. The solid curves are the without CD results, while the dotted and the dashed lines are the second and first order CD approximations. One can see that it only lowers the kink number for fast quenches. However, as the driving time gets longer and longer, its effect is lost. The dynamics becomes insensitive to the CD. It happens approximately at this plateau part. This plateau part perfectly mirrors the fact that we have an exponentially small gap. Because once the driving time is in the plateau regime, all the higher all the excitations to higher excited states are suppressed. CD is not needed. CD would be only needed for assisting the passage through the exponentially small gap. However, it's not able to do so. That's why we have this exponentially extending plateau, meaning that it extends, it gets longer and longer linearly on a logarithmic scale as the system size is increased. Because the gap was exponentially small, the driving times becomes exponentially large. And CD is, again, this regime is insensitive to the local expansion of counterdiabatic driving. A further example of this feature is that the energy gap at this critical point remains also exponentially small once the driving time is increased to this plateau part, as can be seen in this plot. For the first and second order CD expansions, we have a much slower exponential decrease for fast drivings, for short driving times. However, when the driving times gets into the fast quench to this plateau part, we have the same exponential decay of the gap as without CD. The failure is because of the following. The local expansion is blind to this bottleneck because what should be done is to connect the two macroscopically different spin configurations, or to tunnel adiabatically between the two edge states lying far away from each other in the one-dimensional hopping model. While this expansion with the minimization approach, with the variational approach, rather tries to mimic simultaneously the exact CD by simultaneously suppressing all transitions between all pair of states. But after a while, after increasing the driving time, they are not important anymore, just the bottleneck, which is not addressed properly in this local expansion. For this reason, we introduce the QBCD approach, the quantum brachistochrone counterdiabatic driving, which relies solely on the approximate knowledge of the energy gap and the approximate knowledge of the ground state and the first excited state. With this approximate knowledge, we can determine the exact CD for just the ground state and the first excited state, which ensures the perfect tunneling passage between these two edge states or between the two spin configurations in the spinor language. What does it mean to have approximate knowledge? For example, in our spin glass toy model, we use some analytics as discussed in the paper in detail. We can have analytical approximations, but one can do orders of magnitude faster numerical search for these eigenstates and for the energy gap. And let's see the results, what it can achieve. As we can see, this exponentially extending plateau part induced by the exponentially small gap is really lower to a finite value. In this limit, when we say 1/2 King number, that implies approximately 1/2 final fidelity in the thermodynamic limit. And this is achieved instead of zero fidelity by this QBCD Hamiltonian. The energy cost is also more advantageous compared to the local expansion, as it remains bounded as quantified by the norm square, while for the local expansion, the norm square grows linearly with the system size. So it diverges, not so feasible for experiments. This is exemplified in this plot. This is the approximately linearly growing cost of the local expansion, and this is the constant convergence towards a bounded constant value for the QBCD. As I said, one can also use numerical search for determining the critical gap and the critical eigenstates, as we also did, tested the QBCD on a non-integrable model. That is the 3x ORSAT problem, which is a very funny problem actually, because in classical optimization problems, it describes the solution of equations of systems modulo 2 such that each classical bit is either 0 or 1, and each bit appears in exactly 3 clauses, 3 equations, or in the spin language in 3 interaction terms. We compare the QBCD and the first order local counterdiabatic expansion, which, because of the Hamiltonian is already 3-body, is also composed of 3-body terms. We measure the fidelity because of system size restrictions, and we can see that there is negligible difference between the no CD and first order CD results, showing an exponential decay, while surprisingly the fidelity remains approximately constant with the QBCD Hamiltonian for 2 different driving times. And as I said, one can also show further advantageous features of this QBCD. For example, it's robust against determining of the properties of the critical point. It's robust against deviations from the exact critical point, as exemplified in this plot showing the minimal gap scaling for the spin glass toy model. The red dots correspond to the analytical approximations, missing the critical point by almost 10%, while the black squares correspond to purely numerical search for the critical point, missing again more than 10%, still preserving a polynomial decreasement compared to the exponential one without and with local CD. And even further simplification or truncation scheme can be performed, exemplified by the XORSAT and in the previous plots, namely that we only left the 0.25% of non-zero elements, which achieves such a sparse matrix that we would end up with in case of 3 or 2-body CD interactions, which teaches us a very important lesson. It's not the locality that matters, but to involve the correct multi-body interactions. So even though they are still not local and hard to implement, at least it really shows that you don't need to consider all the multi-body interactions, because if you would consider all of them, you could not end up with such a sparse matrix which only has the 0.25% of the original non-zero elements. For L equals 16, that's really agrees well with the number of non-zero elements with the 2-body interaction CD term. So a quick conclusion of the first part of the talk: local CD expansion for exponentially closing gaps is ineffective, and a novel approach, the QBCD, it can really achieve exponential speed up, a new truncation scheme, and is also applicable to a real NP-hard problem. Furthermore, it's robust against missing the exact critical point, against deviations of the properties of the critical point. In the next part, in the second part of the talk, composed in the second paper, the aim is the same, speed up, but the tool is different, tailoring a single control parameter. The systems under investigations are also a little bit different. They exhibit a second-order quantum phase transition, which are important of preparation of topological phases. Also, tailoring a single control parameter acts faster, acts better, achieves faster adiabatic dynamics than CD, usually, as you will see. And also, further motivation is that local adiabatic condition is not a many-body-like condition. So many-body extension is highly required for the usual local adiabatic conditions. Our generic platform example is the transverse with Ising model, spin chain with closed boundary condition with ferromagnetic couplings and uniform transverse field, which can be mapped to independent two-level systems labeled by the momentum or mode. It has a critical point second order phase transition at g equal 1 if j is set to 1 with the critical exponents being z and nu equal 1. This is a good model. Everything is 1. The critical point separates the paramagnetic and the ferromagnetic phases, the simplest version of topology, color trivial phases. A very quick recap how the dynamics of this quantum phase transition can be quantified. For linear protocols and for slow drivings, excitations identified as kinks are generated by the Landau-Zener transition probabilities independently in the given modes, as exemplified in this plot. This transition happens around the minimal energy distance, identified as gap, and many times referred to as avoided level crossing. So at this point, these Landau-Zener transitions induce excitations. Adding them up, one ends up with a scaling of the total King number of 1 over square root of d, t, which agrees well with the conventional result of the QBCD mechanism. This King number scaling is a very useful quantity because it can make strong predictions on how the adiabatic time scale will look like. In particular, faster decay implies earlier onset of adiabaticity. The onset of adiabaticity, where fidelity departs from 0, the final fidelity departs from 0, is identified when the King number reaches the value of 1. When you are remaining with one King below that, you start to have final fidelity. So the aim with this tailoring of a single control parameter is a faster decay of defects. While local CD only lowered, as we saw, the fast quench or the excitation values for fast quenches, tailoring a single control parameter drags the whole curve of the King number as it makes it faster, induces a faster decay, so that also an earlier onset of adiabaticity will happen. However, earlier approaches were not so complete, to mention the least. They were mostly heuristic, with no analytical insight and missing even the simplest many-body effects. To mention the least, optimal nonlinear passage, relying on the Kibel-Jurek scaling law, which achieves a faster decay, but not the best possible. And then local adiabatic conditions, the Serfroland or the quantum adiabatic brachistochrone approaches. Both of them tries to minimize the local adiabatic condition. The first, by bounding it with a given constant. The second, by minimizing it in terms of an action, according to a least action principle. However, as we showed, both of them failed to drive effectively the quantum phase transition of the transverse field Ising model. As a matter of fact, they don't even exhibit Kibel-Jurek-like power law behavior, because they rather exhibit an fast quench constant plateau, extending as L square and L for the Serfroland or local adiabatic driving and the quantum adiabatic brachistochrone approaches, as can be seen here. Rescaling the time argument with L square and L for the two approaches achieves very precise scaling collapse of the kink density curves. This implies then there is a fast decay. However, altogether they imply an onset of adiabaticity scale of L to the power 2.5 and 1.5, meaning that the Serfroland approach, the true local adiabatic approach, performs even worse than the linear driving, which is very surprising and funny in some sense. The reason is that local adiabatic condition in these models and most of these critical models only takes into account the zero mode, the lowest lying mode, because they govern the local adiabatic condition. This works in the following way, like exemplified in this plot. It tries to go super slow around the zero mode, only considering the zero mode. And then once excitation is in a zero mode, is avoided, it feels that it's free to speed up arbitrarily. So as system size increases, there is a sharper and sharper super fast jump, missing all the higher excited states, which get excited almost surely. That's why, for example, this LED or self-round approach leads to even worse performance than the linear protocol. To cure this problem, we introduced the non-adiabatic quantum optimization approach, where we realized that the true source of defect generation are the Landau-Zener transitions at the avoided crossings, as I showed in the previous schematic plot. It's again a least action principle, but the action is composed of the sum of the Landau-Zener transition probabilities. It can be cast into a convenient time integral form from which one can derive the non-adiabatic quantum optimization control equation. Solving these equations, plugging the protocol into the transverse with Ising model achieves 1 over t very fast decay of decays, which is the fastest, as exemplified in this plot. The first two curves in the plateaus are the already mentioned local adiabatic drivings. Then comes the linear protocol decaying as a 1 over square root. Then the extended quantum adiabatic brachistochrone that I didn't have time in this talk to talk about, optimal nonlinear passage, and the best, the fastest, and the shortest onset of adiabaticity identified, shown by this line, is by the non-adiabatic quantum optimization. And as I mentioned many times, the onset of adiabaticity, now there is also a plot about that the onset of adiabatic timescale, the timescale when the fidelity starts to be finite, only grows linearly for the non-adiabatic quantum optimization. Slightly faster, so slightly worse performance by the optimal nonlinear passage, as summarized in this table, power of 1.2, and then the opposite order as in the previous defect density plot. Then the extended quantum adiabatic brachistochrone, the quantum adiabatic brachistochrone growing as 0.1 half. Then the linear scaling quadratically, and the worst is the true self-round local adiabatic condition approach, 2.5. You can see two more here, which I'm going to turn to average and best crab. The crab is the abbreviation of a purely numerical method, chopped random basis optimization, searching in a Chebyshev polynomial expansion for the best for the coefficients, achieving the smallest possible king number. It is a stochastic search, so one should distinguish between the best and the average crab. It's very interesting. We were very surprised that, first of all, it's very restricted, just to a few hundred spins for which one can run it in a reasonable time. We ran it for 1000. It took a week on a cluster, and the performance was not even as good as the optimal nonlinear passage. The result was the average result of this crab is t to the minus 0.75, worse than the optimal nonlinear passage, and the best is also a little bit worse than the optimal nonlinear passage. It can be seen here. This is the average result from the purely numerical optimization, the crab, and the darker blue is the best. One can see that the green, the optimal nonlinear passage, goes a little bit faster. And again, just to show it better, the non-adiabatic quantum optimization goes even faster. And as a final exemplifying plot about how the protocols look like compared to each other. This is kind of the sudden adiabatic, completely adiabatic sudden result from the self-round or local adiabatic driving, which is the worst. And then even though there is small difference between the non-adiabatic quantum optimization, the optimal nonlinear passage, and the crab, these small differences matter a lot, as we can see from this plot. Additionally, because it's a purely numerical search, the crab is not even symmetric. one doesn't require that, just to search in terms of all possible protocols expanded in this form. And then the extended quantum adiabatic brachistochrone is getting closer to the linear, which is the last one, which is the simplest one. As a final result, as it cannot only be studied in terms of a transverse Ising model, we also generalized it to the long-range Kitaev model, which describes really a second-order phase transition point separating a topological and a trivial phase. This is a P-wave topological superconductor where the topological phase is identified by the presence of a Majorana zero mode. It has different scaling regimes, non-equilibrium scaling regimes, as pointed out by this nice paper of Niccolò Defenu. One can have a Kibel-Jurek scaling regime where the power law of the hopping and the pairing term, given here, satisfy these relations. And here one has this decay of the defects for linear driving. If one applies our approach, gets a much faster driving, a much faster speed up than quadratic, as can be observed here. And it also surpasses the performance of the optimal nonlinear passage applied to this problem. The really interesting things, after discussing briefly that for weak pairing achieved for this power law interaction exponent, where the system becomes almost identical to a transverse Ising model. So, but after this, really the truly interesting regime is a dynamical scaling regime, where the hopping power law becomes small enough to destroy the local structure of interactions. One has really long-range behavior. The Kibel-Jurek mechanism loses its validity, and so the optimal nonlinear passage, for example, is inapplicable because that relied on a Kibel-Jurek scaling. But our approach for this dynamical scaling regime of crossing a topologically non-trivial second-order phase transition point still works and provides a reasonable speed up in terms of the decay of the defects, as is exemplified in this plot. As the alpha, the hopping interaction power law increases, so it becomes weaker and weaker, the decay is faster and faster for both the optimal, naively applied optimal nonlinear passage and the non-adiabatic quantum optimization. As a final slide, because I'm a little bit over time, is our final result, how it can be tested or applied to a non-integrable system, because so far we used the integrable and analytical properties. Well, for this, we considered the spin chain, but such that we made it disordered via introducing Gaussian distributed couplings into the nearest neighbor interaction terms, and we also introduced an antiferromagnetic next to nearest neighbor interaction. We realized that the non-adiabatic quantum optimization can be used as an ansatz via the long-range Kitaev model results. Namely, we could compute numerically the scaling of the ground state gap with respect to a system size, and we identified this power law as 1 minus beta, starting from the general form of the control equation for the long-range Kitaev models, which I'm not presenting here because they are very long, but not so hard to solve numerically. So via this ground state gap scaling, identifying the beta and taking the simplest, just to have really the simplest and most robust prediction, alpha, namely infinity, we tested how this control equation performs for this model. And again, compared now only to a linear, a much faster decay of defects, or excess energy in this case more generally. More faster excess energy decay was observed for both 14 and 18 spins that we could reach within reasonable timescales. So a quick last conclusion of the second part. Again, local approach is not working for crossing second order phase transitions when we are tailoring a single control parameter, and we actually proved why they are not working for a transverse Ising model. Instead, we introduce a non-adiabatic quantum optimization, which directly attacks the source of defects and outperforms all previous approaches, either numerical, analytical, or heuristic Kibel-Jurek based methods. We generalize to real systems where really important or interesting topological phases are separated by quantum phase transitions. They were the long-range Kitaev models, and we also showed how it can be applied as an ansatz for a non-integrable model. So that's the end of my talk. Thank you very much for listening to it.
Great, thank you very much, Andras. A virtual round of applause from me on behalf of everyone in the audience. Lots of interesting things, and I'll now open it up for questions. So if anybody has a question, either unmute yourself or speak up or raise your hand or any other conventional method. Maybe I'll start with traditional chair's first question. So going back to your first half of your presentation, where you're talking about this quantum brachistochrone counterdiabatic driving.
Yes.
There were some, was it third order interactions I saw?
That's the model for which I tested. I wanted to make as broad picture as I could. So this is
I see. Okay.
This is the 3x or SAT model, which has this Hamiltonian three-body interactions. It's similar to
what sort of order, what sort of interactions and of order interactions do you need for your counterdiabatic term in this QBCD approach?
That is hard to test. So that is not aim of this QBCD approach. I just tested that one can construct it with the approximate knowledge of the ground state gap and the ground state and the ground state and excited state at the critical point. And then I made this QBCD Hamiltonian as sparse as I could to still achieve a reasonable speed up. And this sparsing was that I only kept the 0.25% of non-zero elements.
Do you have a feeling for, I mean, are the additional terms XX or YYY or XYZ?
I would suggest, I would guess that it would contain still multi-body terms, but not all of them. Just a few. Just let's say, suppose you take L over two body terms. There are a lot of L body terms. L choose L over two, but maybe you just need one or two. I think that should be the case.
Yeah. It's some work that we've been doing in my group with Sagato Bose's group. Been trying to look at these higher order terms in X. So if you have a cubic X term, then this can enhance the gap. So I was wondering, how similar or different that approach is. There's clearly a lot of commonality there, but unless
if it's exponentially small and it's really the underlying macroscopic rearrangement of the ground state and first excited state, I don't think this finite number interacting terms can amplify the gap. Because if you increase the system size further, the relative weight of tunneling between the distance spin configurations, that decreases to zero in the end. So actually, but we also tried for the spin glass model, for the toy model, the three-body terms. That was called second order. Because you can rule out first order term single body term doesn't give contribution. So what we call first order is two body, what we call second order is three body. Because there's a second what appears. And that effect was again just to make it stronger, that it's not really effective, unfortunately, that the effect is this dotted line which ends to be effective or decreasing the king number once you enter this plateau, which is governed by the last gap.
Yeah, sure. Okay, well, in the interest of time, I'll offer the next question to Viv Kendon. So over to you, Viv.
Hi, can you go back to the slide you were looking at first with the previous questions, where you have the curves showing where you have the plots of the result for this?
This?
No, you've got that one. Yes, that one. Okay. So you've got it. You've got how well the red dots do for this for the method. But what do I mean? 16. I mean, it's big for a simulation, but it's not big for scaling. So it looks to me like it might be starting to turn over. I mean, what do you expect to be able to do here? Is this a problem where you expect an exponential speed up?
Well, I was very hopeful about this because for this XOR SAT, already for a small number of spins, you can see the exponential behavior of the gap. Actually, I'm running for 18 now, but that's the end. Unfortunately, I cannot push it to 20. Sure. I would expect that it turns around. This was very strange to me, but I would expect that it will exhibit, rather a polynomial decay then, based on the results of the spin glass toy model, for which we could go to, we could go to almost 1,000 spins because it's a free fermionic. There's a free fermionic underlying model.
In other words, what you're saying is this is a problem you expect to be able to solve in poly time. It's just that quantum annealing can't.
Yes, I mean, if one can realize this QBCD Hamiltonian with this sparsing, with this neglecting most of the elements, I would expect that, on an IBM quantum computer, for example, for 100 spins, it would still exhibit, that I could guess, it would still exhibit just a polynomial decreasement of the fidelity.
Right, because I'm trying to see if you're, I mean, here if you've got an exponential speed up, but I'm just checking that the problem itself is not exponentially hard, right?
That's right. I wanted to say a word about it during the presentation, but then the time was short. So this science paper has a title, Being Glassy Without Being Hard to Solve. This is a very particular problem which classically can be solved by Gaussian elimination, but still it is a glassy phase in quantum annealing and an exponentially small gap. But that's right. So in the paper that we are going to resubmit to PRX Quantum, and these are the new results. I'm also exemplifying this QBCD for the max cut problem, which is truly NP hard also in a classical sense.
Yes. So yes. So because one way to test that we've been using for a couple of things in collaboration with the people in Jülich is if you've got curated hard problem instances around sort of 16, 18, 20, then you can see the different, you can see that it's going to turn over more quickly because you're only testing on very hard problem instances. So it depends what problem you're using, but that's one way to deal with the fact you can't simulate much larger problems. So
okay, so you could see traces with similar approaches that it will turn over and turn back to the exponential one.
Yeah. If you have, and there, so for just for Sherrington Compatric spin glasses, there are curated hard problems, and I think one other, a max something or other, that is also exponentially hard. They are available.
But I'm sorry, I didn't hear properly. What was the approach? It was a local expansion of CD.
Oh yeah, no, this wasn't this kind. We've just been testing with quantum walks. So
I see. Okay.
So multi-stage quantum walk. So we're parameterizing the anneal in a very, very different way and looking at heuristics around that. So what you've done is probably relatable, but not very directly.
I chose this problem because in many of the numerical checks that investigated these problems, the max cut and a 3 XOR SAT, they stated clearly that this exponential power law is this exponential coefficient is the same for 16, 18 as it is for 200 with quantum Monte Carlo. So yeah, that's why I am, let's say, hopeful that this constant behavior won't turn back to the exponential, possibly just to a power law.
Right. Okay. Yes. But yeah, as I say, we had something quite interesting in the setting we were working in, and then we made sure to find some curated hard problems so that you could see at the point where you hit the limits in terms of the approximations you'd made will become more and more expensive. But you might, I mean, it depends on the problem always.
Yes.
So yeah. exactly. Very nice work. Thank you.
Thank you very much.
Good, thanks, Viv. Any other questions for Andras? If not, let's thank Andras once again for a very interesting and thought-provoking presentation. A round of applause from me.
Thank you very much. It
Everyone.
was a big pleasure for me to
And
present this.
I look forward to welcoming everyone to next week's INQA online seminar. Thank you very much. Bye-bye, everyone. Enjoy the rest of your days.
Bye.
Bye, goodbye, thanks.